1176 times 10 to the power minus 9 divide by 133.76 times 10 to the power minus 9, and then divide by 2 times 10 to the power minus 3. Okay, so this will come out to be 5 power 3 multiplied by 1176 power minus 9 divided by 11133.76 power minus 9 divided by 2 power minus 3. So it's equal to 21.979 times 10 to the power 6 Pascal. Okay. What I'm going to say now, okay. Only one student cannot answer because I explained to the student that the student understand it. Okay. For $20, can you think why this works? For $20.
$20.
Hey?
I want $20.
No, I told you the answer already.
But I challenge your rules. I deserve the $20 too.
Okay, I will check your email. Get ready to receive a direct debit. Okay, I'll check what's your. So check your McMaster email and make sure it's not. It is not. What do you call it? It's not full. Okay, or not the email sent to you. You cannot do direct debit. Okay. Anyone except Mariam, please.
I think it's because of symmetry. So the L shape that we just analyzed is similar to the same L shape we analyzed at the top.
Yeah, but the question to you is why we only analyze the L shape?
It's because we're extending from the shear center.
Huh?
Is it because we're extending from the shear center? Like we're following the shear flow out from the shear center?
Mustafa, say it again.
Like the line in the middle, the shear force axis, we're extending out from that, following the shear flow to D.
Yeah, but why the question now is this. Okay, what I'm looking for is what rule is it? Okay, why we don't consider the entire structure in orange? Like
Is it because rule 3 says analysis starts at y max, so we start at like y max, which is the very bottom, and then we go to D, but the other web has nothing to do with D, so we don't include it.
Why?
Because D is not on the other web, so we only include the flange and the web that D is on it.
Yeah, but what is the indication?
The shear flow is going the opposite direction.
Say it again.
The shear flow is going the opposite direction.
Adam, you are right. Adam. So what? So when the shear flow is going to the opposite direction, so what?
It's no longer.
Why? Okay, now I'm going to ask you. Why won't it work when the shear flow goes in the opposite direction?
So it's no longer increasing the stresses. It would be decreasing the stresses at D because it acts in the opposite direction. So it's like would it be like a canceling effect?
You are not 100% right. You are 58.2% right.
I'll take it.
Okay, but Adam, I will not waste time. Adam will get 20 from me, and so is Miriam. Okay. When we derive these 4 rules, right? It got me thinking. When we derive these 4 rules, now what Adam say is right already. Okay, what Adam say is right is what he observed. Again, we have to relate this mathematically. How how the 4 rules are formed. When we form the 4 rules, right? We took it from a beam, right? Which is a centroid. And this is our shear force. The Q is only what? The Q is only one direction. Okay, it's like the bend, right? One direction, right? over. So relative from the centroid. I repeat again, relative from the centroid. Okay. So, but for this case, right, below the centroid, you have the shear flow coming down in one direction. Horizontal does not mean reverse. Okay, horizontal does not mean reverse. Okay, so horizontal is fine. Okay, but it went reverse direction. Okay, and that's wrong. We cannot apply. Okay, we cannot apply. Okay, so we cannot apply this anymore. Okay, this is wrong. This is confirmed wrong. And the confirmation wrong, the criteria is the value got from the top and the bottom are not the same. The only way that it has to be the same, it is using just a shear flow in one direction. Okay? Right? Now, question for you guys. Okay, you see that yes or no. Once it go reverse, it will not work. Okay, it will not work because the Q over here derived, okay, did not have another Q in the opposite direction. Okay, now, question for you all. Okay, what then if that's the case? What Miriam asked, or also Iman asked, how do we get the value of F? Anyone? After you see all this already, okay, we've seen this. What did we do? We came out with condition why it did not work, right? And we have a criteria why it did not work. Okay, we prove it did not work. The criteria is the analysis, the shear stress analyzed from the top, and the shear stress from the bottom have to be the same. Okay, especially at the center. If it's wrong, there is something wrong with analysis. Okay, so now we know why it's wrong, and now we know, okay, how to make it right now. Now, question for you. Okay, so this part over here that is in the center of the screen is how we make it right. Okay, so now you know the secret. Okay, now not the secret. Now you know the concept. You understand the concept now. Now, question for all of you. How to get the value for point F? What is the area that we're going to consider? Anyone?
Do you
Would it
have
be
to?
the same? Now you go first.
I was going to say, do you start taking the area from point C? Like you start from there.
Point C, it moved away from the F region already, right?
Okay.
Right. So how to find point F?
I was gonna say like the same L shape, but instead of starting from D, you start from the other black line. You know what I'm saying?
Start from point what?
See,
So
you
I
see,
would
like, so
okay.
and you know for
Okay. This let me clarify. Okay, Vidu, you speak like a lawyer. Okay.
come on, sir. First it was Shanker, now it's a lawyer. Come on.
So you are a barrister. Okay. So I want to find point F. What is the area I'm going to consider? Is it point C or point B?
Okay, I was gonna say neither of those. Okay, I think I was
No,
gonna say
no,
the
no.
same.
You see, I knew you were a lawyer. Neither. It's either guilty or innocent,
Oh,
but you tell me guilty or not guilty, not
okay,
necessarily
no.
innocent.
Actually, no. I think if you're talking like that, it's gonna be from point C, like the C to the F would be like the area you consider.
No. Okay. It's going to be from point where? Okay. If I'm going to start from point C,
Yeah.
right? If I have an equivalent position, okay, and the position at point C and at point G, I'm introducing at point G, right? They have the same location relative to the centroid, yes?
Yeah.
The values has to be the same. But if you say it's from point C, what will happen?
They're crossing the centroid, so it breaks rule number 4.
So it's not the same anymore, is it?
Yeah.
Okay, so it's going to start from point B. Okay, so the shear stress. So now we're going to find point F, the shear at point F. Okay, so the shear at point F. Okay, so let me sketch point F. So point F is something like this. Now, I like to also say something. You guys are not wrong to say that you have to consider point C. And I'll tell you why that is not the case. Okay, I'll tell you why that's not the case. So over here, so from the bottom to here is 14. This is the point we want to find. And then the distance from here to here, right? The distance from here to here is 25. Okay, so the whole thing, you add another 1. Okay, so this is what we want to find. Okay, so Q now is equal, the width is equal to 2. The depth is going to be 14. Sorry, I should stop doing that. Okay, so we know from here to here is 7, right? So from here to here is 25 plus 1 minus by 14, right? So 25 plus 1 minus 14 is 11. So this term over here is 11. So will be equal to 11 plus 7. So it's equal to 11 plus 7 times 14 times 2 is equal to 504 millimeters cubed. Okay, so Q at point F. So finally, the stress at point F is equal to 5 times 10 to the power 3. 504 times 10 to the power minus 9. So I put this equal to 504 times 10 to the power 9 meter cube divide by 133.76 times 10 to the power minus 9. And then you have 2 times 10 to the power minus 3. And this analysis is white flange. So what we get from here is 5 power 3 times by 504 power minus 9 divided by 133.76 power minus 9 divided by 2 power minus 3. The answer is 9.42 times 10 to the power 6 Pascal. Now, that is a true value. Okay, mathematical proven, concept derived mathematically. Okay, now the question is now this. You are not wrong to say, Eugene, why don't you? So, okay, the most obvious is this, okay? There's a new boundary condition for thin wall, okay, thin wall. Okay, not just thin wall, okay? Thin wall, okay? For thin wall with Q in both direction, right? So one more rule we have to consider is only consider rule in consider Q in one direction only. Moving towards the shear force axis. Okay. Okay. So this is the other rule. So that is why, right? Over here, we only consider one direction. We don't consider this direction at all. We don't consider this direction at all. No. Okay. Now, Vidu-san say, why don't we stop at point C? Okay. And that is what I thought also. Okay. Why don't we start at point C? This is because, okay. Now I'm almost done. Okay. I'm almost done. I did not explain this well the last time. Okay. And it's my fault. I think, as I said, my wife always tell me that I get too excited. I can't explain things. If we consider, let's say, if we consider a point over here, right? the area we look at is always this area because it's going out towards the where? Going out from the shear flow axis. Yeah, shear force axis, yes or no? Right? So when we look at point D, right? Point D, right? We allow the flow to come back here. Okay. So it will go towards the what? Go towards the shear force center. Okay. So that's why we consider this area. Now at point F, right? Again the area is from the shear flow, the shear force center. So at point F, this is point F. So if we go outwards, this is the area that we consider. Okay, we stop here because once we go beyond, okay, point F, right? Point F area, right? The flow will not be affected, not the flow. The area of analysis cannot be up to point C because at point F, the major web stops here. Okay, that's why you cannot go to point C. Okay, and I did explain before at point B, right? They call it equal to 0. No, I've proven to you also it's not equal to 0 last week. And last week, I proven to you that it's not equal to 0. Where is it? And let me point, where did I prove that? Thursday, Friday, right? I derived to you that at point B, it's not equal to 0. There's a small value. Okay, there's a small value over here, and the what? The stress is equal to 37.38. Okay, but relative to kilopascal to megapascal, the shear stress at point B is close to what? 0. Okay. So once again, that is the explanation. Okay, for this. Okay, for the concept on how to get a point at F. Are you all clear? Anyone, any questions first before I let you go? Anyone? Or you can, if you have another class, please go. But if you have questions for me, okay, please stay behind, please.
What if
Eugene? Oh, sorry.
Yes.
I was just wondering, would we ever get a question like this that isn't thin wall analysis? And how would we approach that?
Say it again.
So like, because we're doing thin wall analysis.